Cool. Okay. All right. So again, thank you. Welcome back to our class. So today for the lecture, we'll talk about different security properties, different security ideas, and there's a a bit of definitions and terminology which might be not the most exciting, but this gives us sort of like a common framework to talk about different security issues, and then when we start to analyze the quantum computers. So this week we'll talk mostly about classical security, some things like these definitions, and then we'll move on to more like quantum computing part in the future meeting. So for some definitions, actually kind of want to start about sort of talking something maybe obvious that when you design a computer system, whether it's classical computer or a quantum computer, most people or most companies or most researchers focus on performance, cost, power, area. These are common metrics that you use to design a system, and then these metrics I think are very nice because you can quantify them. So when you design let's say a quantum computer, if you have better fidelity, you can provide some number for the fidelity of the qubits, and better fidelity means better quantum computer. It's easy to quantify it. So I think that's why a lot of things focus on performance or area, because again you can give it a number. Now security. There's a lot of benefits to security, and that's why I think we should study it. But the problem is that we cannot really quantify a security. So when you propose a security mechanism, or you implement some security feature, or let's say you spend 20 hours reviewing code to find security bugs, at the end you cannot quantify how secure the system is. And because you cannot quantify how secure the system is, well, there are two things. Well, first, that's why we turn into this threat-based analysis. We define different threat models. But I think that really the practical thing is it's really hard to is my thing better than your thing? It's really hard to compare because you cannot quantify it. So this aspect of security, whether it's quantum computer security or classical security, is sort of very, very subjective. That I found this bug, or I looked at the code for a week, I didn't find any bugs. It's hard to quantify, which means it's hard to compare things. Is it better? Is it worse? And then if you're in some sort of a business or a company, it's really hard to sort of sell security because yes, if somebody hacks your system and exposes your data, clearly something's wrong. But if I pay extra for this more secure web browser, is it actually more secure? I don't know. It's hard to quantify. So that's why instead of trying to quantify the security, we focus on the threat-based design, which basically means we have to consider different attackers and how they could exploit the system. And I think sort of one assertion or kind of one thing we want to promote is that the security design, although you cannot quantify it, it should still be done in parallel to the cost and performance. One common thing I think that you'll find both in software and hardware is that if there is a security problem and then you fix it later on, typically it reduces the performance, or it increases the cost, or it increases the area, or increases the power consumption. So adding security features after you have designed the system usually makes these quantities worse, and then it's harder to sell your product. Like I don't know if a lot of you heard about like Spectre and Meltdown. These are maybe not. I can share some things. It's a now kind of old security problem with classical computers, but basically the idea is that the classical computers use some optimization features to run faster, but that can result in data leakage. And then to mitigate that, you would have to turn off these performance features, and then it makes the processor slower, and kind of nobody actually wants to implement the defenses because things become slower. So that's why we want to kind of study the security in parallel to the performance. And then when we talk about threat-based attacks, there's the threats, which is more like a big class of problems, and an attack, which is one specific instance. So side channels are a threat, but a specific power side channel on some supply pin to the DRAM would be a specific attack within that threat class. So you have threats, but then you have specific attacks, and we want to defend from those attacks, from those threats, but then we have to, understand what do we mean by security. And then here are the the three main ideas we already talked about: confidentiality, integrity, and availability. So do you remember, anybody want to remember what any of those means? Uh-huh.
Reality is making sure people should access.
Exactly right. You shouldn't be able to, only authorized people should be able to access some data, or only authorized programs should be able to access some data. How about integrity? Anybody else? Yeah.
Is that the data is not yet ready.
Yeah, yes, or that, unauthorized people should not be able to change the data, or unauthorized programs should not be able to change the data. How about availability?
And that's the authorized people should be able to access.
Yeah, exactly right. So yeah, the system should be accessible, and there is so these are kind of the repetition, and in each case we talk about, there's an unauthorized individual, but this could be, a program, a process, something, doesn't have to be actually a person. And then there's you can remember as CIA, confidentiality, integrity, and availability. And all of these mention sort of some sort of unauthorized access. So this leads us to access control. So in access control, we have these two useful definitions, which is authentication and authorization, which are two related but two different things. So perhaps self-explanatory from the name, authentication is basically a way of identifying someone or something, a password, API key, access token, something that basically identifies who are you talking to, or what program or what process you're talking to. And then once you authenticate something or someone, then you have some sort of authorization, like what can they actually do. So for this, for this confidentiality, for example, is this Bob, and can Bob actually read the data? Or for integrity, is this Alice? Can Alice actually write the data to change it? So you have to have both authentication and authorization, and then so access controls those two things together. So ensures that only authenticated users, programs, whatever servers who are authorized can access or modify the data. So this is kind of the authentication and authorization. Sometimes there's a mix-up. You sort of maybe you authenticate a user, but then you sort of, once authenticated, they can do everything. So if you mix up authentication and authorization, people who are authenticated might be able to do things they shouldn't actually be able to do. Like, maybe you're able to log into a Northwestern system, but just because you're a Northwestern student doesn't mean you can do everything within any Northwestern system. And then there's a AAA acronym for the AAA insurance. Anyway, just to remember, those. So this is just kind of like a very quick table review of, have the confidentiality, integrity, availability, access control. There are also things like attribution. So basically, that's actually quite important if you do some sort of analysis of a security attack. Can you attribute it to some specific individual or software? If you cannot, maybe there's an attack, but if you cannot attribute it to anybody, then you can't, hold anybody responsible. And then there's accountability. So somebody has to be responsible for the vulnerabilities. But if let's say if there's a bug in some software, but you cannot attribute the bug to any specific thing or someone, then you can have accountability. And then we have things like audit to keep logs of what's happening in the system. Attestation, we'll talk a little bit about attestation in terms of, for example, quantum computer controllers later, but basically the attestations that you prove to a remote party that you are somebody, or you did something that you're supposed to do. And then non-repudiation is very interesting. Basically, that ability that you cannot deny that I send some instructions, and then I shouldn't be able to deny that it was me who sent the instructions. And then I think there's also a lot of important interest in anonymity and privacy. So again, protecting, who's keeping the identity secret, or protecting your personal information. So in this class, we'll mostly focus on security, like security mechanism. But once you have security mechanisms, then you can provide things like, for example, privacy. Like you cannot provide privacy without some security mechanisms, but security mechanisms themselves are not enough for privacy. So there's like a small distinction between security and privacy that builds on top of it. Um, okay, and then another another definition, very also sometimes um, maybe mixed up a little bit, but also important is trustworthy versus trusted. So basically, whenever you have a system, you're trusting some parties or some some programs or some mechanisms to do their work, and then you also but are those things actually trustworthy? So so trustworthy basically means that uh, somehow you verified something or you proved something or you have some evidence to kind of ensure that the system is designed to be dependable and provide the properties that it's supposed to do and does nothing malicious. So basically it's I know it's trustworthy, it's good. But the credit related is trusted. So trusted means that you trust that system or program or software to enforce the security policy. But the key in distinction is that just because something is trusted does not mean it's trustworthy. So, I don't know, the classical example is like in a general. So a general is trusted to be, in charge of things, directing things, but maybe the general is actually spying for another country and they're not trustworthy. So, or maybe a better example, I don't know, are you familiar, for example, like Intel trusted, sorry, SGX or like secure execution extensions for Intel processors? Uh, if not, okay, I'll mention this a little bit later. But for example, uh, most of the computers have features inside their processor to protect the data. For example, they encrypt the data in the memory so the data cannot be accessed. So the Intel as a company is trusted to implement these security encryption mechanisms correctly. But maybe Intel or somebody within Intel is not trustworthy, and then the actual implementation might be incorrect. So that's a kind of an important distinction. So yeah, a trusted system may not be trustworthy is the maybe the takeaway message. And then very important and related to it is the what we call a TCB or a trusted computing base. So basically TCB is everything that you trust for the system to work correctly with regard to security. So TCB or trusted computing base is all the software and hardware that you depend on the system to work correctly. And some of the parts of the TCB may not be trustworthy, but if anything in the TCB breaks, then there's no security for the whole system. And uh, typically uh, um, I said security cannot be quantified, uh, but one thing where we get close to being able to quantify things is can how many components are in the TCB, and then if you can design, for example, a system that provides same security mechanisms with fewer components or a smaller TCB, then that's always better. So if you can somehow quantify the TCB or the number of components, then that could be one metric. But then is a software component same value as a hardware component? It becomes complicated, but that's the TCP. I don't any questions or comments about these? I know it's a lot of definitions, but we'll keep seeing some of them again. So it's good to have like a common language for the discussion. Um, and then so now, right, so we have, different, the trusted computing base that's trying to protect the system from security problems. So now we can talk a little bit about threats and attacks. So again, so threat is sort of like um, a class of things that can damage a system or modify its operation. Threats typically target confidentiality, integrity, or availability. And then attack is the one specific instance of that threat. And then, most in the news, you see a vulnerability. It's basically it's vulnerability sort of like an attack exploits a vulnerability. There was a problem with the system, and then that the attack exploits. So whenever you hear about security, mostly you hear about, oh, there was a vulnerability and some attack exploit that vulnerability. So this is one thing. Another thing that makes secure design kind of complicated is that, when you think about security or when you design security of a system, you have to try to protect from all, from the different threats within your threat model, from all the attacks. But for an attack, the attacker only needs to find one instance of of a threat or one instance of a vulnerability. So sort of you're always at a disadvantage that you have to make sure all the doors are locked, everything is protected, but then the attacker just needs to find one problem in the whole system. So it's a sort of a losing battle most of the time. But yeah, so with the attacks and threats, we have the confidentiality breaches, integrity breaches, uh, availability breaches. So basically, whenever you invalidate one of those properties, then like if somebody guesses your password, that could be the confidentiality breach, or if they modify some data in the memory of the computer, that would be an integrity breach. So these are different things you can focus on. And so, again, more definitions: privacy breaches, anonymity breaches. Well, I think one very interesting thing that we'll also touch upon later in the class is insider threats. So this is sort of uh, I feel like in security we unnecessarily think some people are bad, but anyway, there's this idea that of an insider threat, which basically means that in a company or in a system, there's one component or one person that might not be trusted. So if you think about, for example, IBM as a company has a good reputation, it's kind of a big company, you can trust a company, but there could be an insider, an engineer, or somebody within the company that is not trusted. So a lot of times, when we talk about hardware attacks, or maybe when we talk about like supply chain attacks, there's a threat model, or a lot of people consider a threat model of an insider. So I trust IBM. I don't think IBM is malicious, but there could be an engineer who accesses the quantum computer controller, and could that engineer extract some information from that controller? So again, that's kind of an important threat model that we'll consider. And then we'll also talk a lot about hardware attacks. So hardware attacks might be actually kind of related to insider threats. Basically mean that somebody has a physical access to a machine. So again, if you have a quantum computer or a server inside a data center, um, you know, uh, if you want to have a physical attack, that means there has to be somebody inside that actually can, connect some probe to measure what your system is doing. So hardware attacks inside, let's say, data centers or quantum computing deployments usually imply an insider threat, or it's not listed here, but we also talk about supply chain attacks. So have you heard about supply chain attacks in the news? Not much, maybe a little bit. Okay, so supply chain attacks, like name implies, basically somewhere in the supply chain. So, for example, when you're running some code, somebody wrote the code, maybe they use libraries from some other place, they put it all together to create the software, or when you make the hardware, you buy components from different parts, from different places. So supply chain attacks basically means that some, component is malicious, or some software part is malicious. So for example, again, maybe Apple is not malicious, but they bought a memory module from some company X, and then the supplier for the company X put something in the memory module. And then so even though Apple doesn't know anything is going badly, through the supply chain, there was a bad component introduced. So through supply chain attacks, you can modify some hardware, which could lead also to hardware attacks as well. And then there are software attacks. We'll talk about software attacks. Those usually mean like remote attack in our case. So if you're connecting to a quantum computer, I'm here submitting some circuit to run on an IBM machine, that will be most likely a software attack, where there's a malicious software that you send to the machine. And we're not talking about like a lot of people work on protocol attack, like figuring out like some problem with a protocol, or breaking network things. We will not consider that here. We kind of assume networking is okay, but that's a whole, you can do a whole PhD on protocol analysis and attacking protocols. Um, um, okay, any questions about these terms? Yeah, just a little bit dry, but hopefully, yeah, can just kind of we'll become familiar with them and use them quite a bit. And then so now coming back to kind of countermeasures and defenses. So since we have different attacks, we want to find out come up with some defenses and countermeasures. So countermeasure basically uh, some action device or some strategy of something of protecting against the attack or responding to attack, and then defense is actually taking that action to defend the system. Okay, so now just kind of as a final review, in the end, we have a threat model which will consider all of those things and specify what type of threats that the system defends against which, and also most importantly, the things that are not considered. So the threat model basically limits the threats and the problems that you're defending against, and you can never defend against everything. And then also, the threat model it's very subjective. Like, for some things people can agree on threat models, but for some threat models you might not get two people that agree on the same threat model. So this is sometimes a non-engineering issue of just defining a threat model. It's totally subjective. It's more just conceptual. Okay, and then this is I borrowed from one of the books, but this is sort of a design methodology considering security, which I think is not much different than a regular design methodology for any system. But the key parts are, you have to, describe the usage, define the security problems. What are you trying to protect against? Define the threat model. So what are the different types of threats, the attackers that you're considering? Then design the security policy, how you're going to defend against the attacks, then actually implement those through different mechanisms, and then sort of try to iterate to see if the system working. And then, like I mentioned, usually when you add some security mechanism, it decreases the performance, increases the energy, increases the cost, maybe decreases the usability. I mean, for example, if everybody's annoyed about, the two-factor authentication, you have to, put in a PIN code all the time. So this is an example where, you're improving the security, but the usability goes down because, every time I want to do something, I have to take out my phone and, type a number, and it's just a trade-off that, a little bit inconvenience, increases or defends the systems from random people logging in. Okay, so now maybe I can jump into different security policy models. Um, I think this is useful to know to kind of understand some things in security. I don't think we'll explicitly be using different security policy models for the quantum computing part, but these are good to know about. So again, so the security policy models specifies a set of rules that outline how a computer protects its information, data, and other assets. And then the security policies are not technical issues. It's sort of, you decide, again here, kind of coming back to here, you design the threat model, you design the security policy. This is really not non-technical, just kind of what are you protecting against, and then creating the security mechanism is actually the technical part of implementing some mechanisms that realize your security policy or that work within a different threat model. But the threat model and the security policy itself is not very technical. And then there's sort of different classical security policies. We have the MLS, multi-level security, and then multilateral security. So the MLS, I guess, long time ago, really inspired by the military, but you can map this to like a typical computing system where you might have like some public data that's available to everybody. Maybe you have some users, maybe you have some system administrators, maybe you have some super users on the system. So in the MLS policy kind of really is very similar to what you see in a computer system, where again you have like some public data, a regular user, you have maybe again an administrator and like an IT person who can control all the computers. And then as we'll see, okay, let's go then to MLS. So in MLS, we define different security levels, and kind of naturally the higher you are, sort of the more things you're able to do, and then the lower you are, sort of less trusted you are and less things you can do. So you have typically, top secret, again, from the military, a general might be able to access, or you might have a top secret clearance, there's there's secret clearance, there's unclassified data. So this is different levels, and then there's a strict hierarchy. So in MLS, top secret is more powerful or has more or also has more trust. So usually the higher you go up, then you become you have more trust. But again, maybe it's not trustworthy, but still it's more trusted. And then so the MLS security defines the different levels and then sort of the relation between them. And then from once you have these different levels and the relation between them, you can define how people or programs at different levels can access data or work with the data. So these are different policies that you apply to MLS. So Bella Padula, again, long time from Department of Defense, I think kind of they defined this Bella Padula policy for confidentiality. So this is an example of a policy that's designed to ensure confidentiality of data, to ensure that unauthorized people cannot access some data. And then BLP has these sort of two rules, the BLP read rule and then the BLP write rule. So I think the best, this kind of summarizes this the best. So in BLP, there is no read up and then there's no write down. So what this means that if you're at a certain, if you're at a certain level, let's say you're secret, let's say your level is secret, that means that somebody at the secret level cannot read from a higher level. So again, a regular, regular user at the secret level cannot read some data from an administrator who's at the top secret level. So this ensures that basically, for the confidentiality, somebody who's lower, they cannot read from an upper level, so they cannot break the confidentiality and access something that they shouldn't, because that the data at the upper level is not accessible to them. And then the no write down basically means that so no read out means you cannot read from things higher, so you cannot get some data that you shouldn't be able to access. And then no write down means that you're not able to write data to a lower level. So let's say a regular user should not be able to write or leak some data to like public, let's say unclassified, something public. So basically this prevents data at a higher level going to a lower level or breaking the confidentiality by either not being able to read from up or yourself to write down. So this is the policy. Can you see some practical problems with this policy? So maybe you've probably heard in the news quite often, people talk about declassifying data. So the connection here or the problem is that basically if you have just the BLP policy, then if you follow the BLP policy and let's say I'm somebody at the secret level and I have some data, if I follow this policy, there's no way for me to share that data with somebody at the lower level. So in the news, when you hear about like declassification, there's some top secret data and if you follow this policy, there's no way anybody would ever see the data. But if you have declassification, you have a special procedure where a data at a higher level is declassified to a lower level, so it can actually be spread to other sources. So this is good for confidentiality, but it's not good for sort of all the data gets top secret and you can never share it with anybody. And then for integrity, we have a different policy, BBAP policy, which is sort of basically the upside down version. So no write up or no read down. And what this means is that, again, integrity is about you shouldn't be able to modify something unless you're authorized to do it. So no write up means that somebody at the secret level should not be able to write at the higher level, which would modify them more secret data, and then they should and then they should not be able to read down. What that means that if there's some data at a lower level, you should not be able to read it because the lower level data might corrupt your more higher level data. So this ensures that you cannot break the integrity. And then so these are two models. they work great, except in cases like when you need to communicate something and declassify data, for example. Um, any questions about these models? Maybe some, okay, self-explanatory. And then, but of course, there are ways around these sometimes, and this is what we will be coming back in the class. So we mentioned a little bit, again, side channels and fault injection. So the way you can think about it, for example, a side channel could be used to break the no readout policy. So let's say that formally I cannot access data at a higher level in the system, but let's say if somebody who's um, observing the power consumption of the computer while it's processing the top secret data could learn something about the top secret data, which basically means they break the no readout policy. So the side channels could be used to break that, or fault injection could be used to break integrity and break the no write up policy. So let's say, some unclassified program or something should not be able to write to a more like a user program should not be able to write to the kernel memory to affect the computer. But if somehow the user is able to, let's say, inject like a voltage fault and make a little glitch in the computer, maybe it actually modifies some top secret data, or modifies some data um, in the computer. And I don't know if you have you ever heard in the news about like row hammer attacks? Um, Maybe at some, okay, I'll share these attacks, and then we'll talk about classical hardware security more. But in a row hammer attack, basically the idea is that in a DRAM chip, when you have a dynamic random access memory in your computer, DRAM is made of a bunch of capacitors, and then physically, if you access one set of capacitors in the DRAM, it might cause adjacent capacitors to flip their value. So even though you're accessing your own data in your own part of DRAM, that physical access by reading or writing the DRAM might actually flip the bits in the adjacent data, which belongs to a different process. So like a user program, they call it hammering, and they can hammer a region of memory, and then now you have some bits that flip like in the page table, and then you compromise the operating system. Or I think a few days ago, there was a row hammer attack on GPUs where they're able to manipulate some data on the GPUs. So if you end up working more in security in the future, row hammer attacks is a very reliable area of research where there's always problems and they cannot fix them. So, but we'll also talk about the crosstalk attacks in quantum computers later in the course, which are somehow conceptually similar to the row hammer attacks in regular DRAM. So there's good connections. Then we also have some so in this the multi-level security, it's more like top to bottom, more like administrator, regular user, unprivileged user. There's also multilateral security, which is more about things within same level. So I think the way, at least the way I was taught, this was sort of more like in a law firm. If you have a law firm and there are different lawyers working for different clients, although they're in the same law firm, if I work for Pepsi, I shouldn't talk to my colleague who works for Coke because we have a conflict of interest. But you can also think of it that, let's say you have different programs within one level, how they should be separated. If one program is handling, um, again, maybe data from hospital A, and program B is sending data from hospital B, there should be some rules on how they can communicate. So multilateral security is about things within on the same level, within the same level. And then to kind of control the access to the data to ensure confidentiality and integrity, there's some definitions like, conflict of interests. So maybe kind of, again, common sense that, these are things from different companies or people data that should not access each other's data. So again, Pepsi has their own secret Pepsi formula, and Coke has their own secret Coke formula, and they should not be, these are kind of conflict of interest. There's a company data set, which basically means data that belongs to one of these conflict of interest classes. So this is the data belonging to them. And then prior read data set basically means that if you access something before you remember it, maybe if you're a human, you'll forget eventually, but if you're a computer, you're not forgetting. So prior read data set basically any data previously accessed by the user or the program that could have been stored in some memory. So sort of basically once you access some data set from some conflict of interest class, then it goes into your prior read data set, and then you're sort of forever, unless you forget or unless you can prove you forgot something, you're forever conflicted because you've already accessed it before. And then there for confidentiality. So again, we have some policies for confidentiality and integrity. And then for confidentiality, there's the Chinese wall simple security policy. And then for reading, and then there's a Chinese wall star policy for writing. Uh, to be honest, I don't even remember where the ideas like star policy came from, but it's sort of classical policies that have been always defined. And again, so for example, for the read policy, you can see, S and a subject S can read an object O if and only if any of the following holds. For example, S has already accessed an object in the companion data set O. So if I already accessed something in that company data set, I should be able to read it again. Or for the writing, a subject S can write an object O if and only if both of the following conditions hold. So like a simple security policy allows, so if you cannot read O, you should not be able to to write it. And then there's, if S can read unsanitized objects, then it's allowed to write to O unless some policy. So these are a set of policies that you would define. And uh, again, like I mentioned earlier, this is the policy that's defined at high level, and then the engineer or the hardware person will actually implement that policy in some mechanisms. And maybe as an aside, you could find, so when you're trying to break things like confidentiality, you might find more like a problem with the policy itself. So there might be a logical bug in the policy. There might be some logical reasoning, or there might be bug in the actual implementation of a mechanism that implements the policy. So in this class, we'll focus mostly on the implementations or problems with the implementations, but similar to like like the security of network protocols, you could analyze the security of the policy. Are there like logical reasoning problems with the policy that, I don't know, on Tuesday afternoon, the third week of the month, you're able to access some data because some weird condition holds true. And then for integrity, there's another Clark-Wilson policy for integrity. And then these are kind of the rules, maybe not so important. But again, now coming back to the side channels and the fault injection. So how can we, so we have these policies that if you follow the policies, you should be able to protect confidentiality and integrity. But again, if you have a side channel or fault injection, that's a way of breaking the policy. So for example, a side channel could be used to break the Chinese wall policy for confidentiality. So let's say even though maybe you're not supposed to read something from another class. Again, if you observe the power consumption of the computation that's being done, maybe you can guess something about the data or the fault injection, like I mentioned, this row hammer problem in DRAM memories. When you're doing some work, maybe you can induce a fault that modifies something in another class, and even though the Clark-Wilson protects the integrity through the fault, you're able to bypass it. So we'll spend a lot of time talking about side channels and fault injection. And I think the key thing here is even though you have a formal policy to protect confidentiality and integrity, these side channels and fault injection can be basically used to bypass that. And then just one slide about just coming back to the access control. All of these policies are based on, you authenticate a user, and then you authorize the user, and then once a user is authenticated and authorized, then they belong to some class, and then you can apply the policy. And then so how do you authenticate your user? So maybe again, common sense, but maybe you've heard of it before. So authenticate based on what you know or what you are or what you have. So like a password, you have a fingerprint, or sorry, I guess have fingerprint. Maybe what you are your fingerprint or your iris or what you have. Maybe you have like a USB key token. So to authenticate somebody, you can use these kind of means of authenticating them. So again, if somebody's correctly authenticated and authorized, and they follow the policies, they should not be able to break confidentiality and integrity unless there's some sort of side channel or fault injection that's used to bypass. Um, any questions? Lots of sorry, yeah, lots of dry definitions, but I think this gives like a common language we can use. Okay, so the rest I want to talk about, just introduce very at high level symmetric key ciphers for protection of integrity, and we'll talk about hashing for sorry, symmetric key ciphers for confidentiality and hashing for integrity. So again, we saw these before: confidentiality, integrity, availability are the different key security properties. And then in this part, how do we protect confidentiality? So one mechanism to protect confidentiality is to encrypt data. And then this is where different types of cryptographic algorithms come in. So if you have classical digital data, you can use cryptography and encryption to protect it. In quantum computing, we have an interesting issue that, let's say, all the data that you send to the quantum computer provider, or that's sent to them some server that manages the quantum computer, it can be encrypted. But then once the server decrypts the data and processes it, or sends analog control pulses to the qubits, or sends laser pulses to the qubits, those analog signals or laser pulses can no longer be encrypted, which means at that point you cannot use cryptography to protect the confidentiality. So there's an interesting problem that once you exit the sort of purely digital network part of the system and get into like analog control pulses, we need some new solutions to provide the confidentiality. But as long as things are in digital form, ones and zeros on the disk or on the network, you can use cryptography for different protections. And we have symmetric key ciphers for protection of confidentiality. We'll talk about in the next few slides. We have cryptographic hash functions for protection of integrity. And then on Thursday, I'll talk about public key cryptography, where you can use digital signatures to provide authentication, or you can use key exchange for confidentiality. So today we'll focus on the symmetric key ciphers and the hash functions. So just as an introduction, so in a symmetric key cipher, like the name implies, there's a symmetric key, or there's one cryptographic key that's used for both encrypting and decrypting the data. So in this picture, you have plain text. So if you haven't taken a security course, usually plain text means whatever data thing that you want to encrypt, something that can be plainly seen, it's not protected, and then you encrypt it using some cryptographic cipher and some key, and you get the ciphertext. So the ciphertext is the encrypted version of your data or your program that ideally nobody, just looking at the ciphertext, you have no idea what the plain text is, because the cipher is designed correctly, and the key, you don't know the key. So and then once you have the ciphertext, if you want to actually get back the data, then you decrypt it with the same key, because this is symmetric key cryptography, and you get back the plain text. So this can be, and this works if it's over the network. Alice encrypts some data and then sends it to Bob, and Bob decrypts the data, or Alice encrypts some data, she puts it on the disk, and then tomorrow she reads from the disk, decrypts the data, and gets the plain text. So this works either over the network, or when you're storing data, or if you have like Intel SGX or ARM Trust Zone, you have some data on your processor, but then you actually encrypt it before it gets put into the memory of the computer, into the DRAM. And then when you read from the DRAM, you decrypt the data, and then the plain text in in the processor. So this can be done anywhere, anywhere as long as the encryption and decryption has the same key. So we'll talk about public key cryptography and key exchange, where if Alice and Bob, so either Alice and Bob have to have the same key to do this, or if they don't have the same key, then they have to use something like a public key cipher to exchange to agree on the same key, and then they can use that for symmetric encryption. And then a concept that's very, very, very good to know, or very important, is a one-time pad. So a provably secure means of encrypting is a one-time pad. And then so what a one-time pad is that you have some plain text, which you can encode as binary ones and zeros. And then to encrypt, you XOR the plain text with a pad. So a pad is a truly random string of ones and zeros. And then once you encrypt with the pad, you get the ciphertext, which is the XOR of the plain text and the pad. So this is the ciphertext. And then to decrypt, you just take the ciphertext, you XOR each bit with a bit of the pad, and you get the plain text. And then so this is a provably secure scheme that you cannot break unless you know the one-time pad. So the one-time pad is sort of like the key here. This is great. This works perfect, except it has a huge problem that your one-time pad, you can only use the one-time pad once, because if you start reusing the one-time pad, you can use some statistical analysis to try to guess the pad. So one-time pad can only be used once, and after you use it, you throw it away, you use a different one. And then also the problem is that the one-time pad has to be as big as your data. So if you have 4 gigabytes of medical records, you would have to have 4 gigabytes of one-time pad, which is not at all practical. So this is probably secure. This is great, but it has a lot of problems. And in practice, for example, the usual, if there's a problem with a practical implementation, it's usually that the one-time pad is not truly one time. Like for some reason, somehow the system uses the same pad again, and that's usually the problem. So since this is not very practical, there are different symmetric key ciphers. There's stream ciphers that sort of encrypt byte of data at a time, and there are block ciphers. They're called block ciphers because you take chunks of data and you take your data, you divide it into chunks, and then you encrypt each chunk by chunk. And then the most famous example is the AES cipher. Have you heard about AES before in some class? Probably. It's standardized 20 years, 30 years ago. It's quite old, but it's quite reliable. So AES is a symmetric key cipher. Oh yeah, standardized in 2001 by NIST after one of their competitions. And I think one important thing to remember that AES is not affected by Shor's algorithm. So as far as we know, so Shor's algorithm cannot be applied to AES, and as far as we know, the best you can do with a quantum computer is to use Grover's algorithm to speed up the brute force search. But a quantum computer will not help you breaking AES. Maybe you need to double the key size because of the Grover's algorithm, but in general, symmetric key cryptography is secure against quantum computers, which is good. But also maybe an open-ended, maybe somebody can design a new algorithm that breaks AES. We're not sure, but so far it's not affected by quantum computers. And just to give, we don't have much time, but just to give you a very brief overview of a block cipher. So AES is a block cipher. That means it breaks the data into chunks. In case of AES, there are 16 bytes. So your data is broken into 16 bytes chunks, and each chunk is encrypted by a number of rounds. And then maybe you've heard about like AES 128, AES 192, AES 256. That basically means AES with a bigger cryptographic key, and then bigger cryptographic key means it's harder to brute force. You have basically, with 128 bits, you have 2 to the 128 possible combinations of keys that you could have. And then so they have the same block size, but if the key size changes, the number of rounds, so it takes longer to do the encryption. And then the way block ciphers, round-based block ciphers work, you have your plain text, your 16-byte plain text, and then you have your encryption key, which is again the same as the decryption key. So if you're doing encryption, you have an encryption key. Then there's a key schedule, which is a deterministic algorithm that takes the key and then breaks it up into either 10, 12, or 14 round keys. And then for each round key, you take your plain text and then you go through each round to encrypt the data. And then at the end, you have an encrypted block ciphertext. And then to decrypt, you do it in reverse. You take your encrypted ciphertext block, you take your AES key, you generate the round keys, and then you apply them in reverse, and you get back the plain text. An interesting aside is that this key schedule is fully deterministic based on the AES key. So, for example, a lot of times when people are trying to attack AES, so you can, for example, attack AES through a side channel. So if you collect enough power traces during encryption, you could actually recover the AES key. But what happens in practice is you don't recover the AES key, you recover usually the last round. So you recover the round key, any of them will work. Typically the last one is the target. But if you can recover any of the round keys, then you can just run the key schedule in reverse and you get the AES key. So just an interesting aside that, let's say when you're attacking something like AES, you don't necessarily attack the AES key itself, you attack one of the rounds. Yes, key schedule is deterministic. And from any round key, you can get the AES key. And then okay, very quickly, I think we're out of time, but the AES has a standard round with these 4 operations, which are kind of standardized operations: substitute bytes, shift rows, mix columns, and add key. And maybe this is not the focus of our class, but just so you see this picture and recognize it. Usually the substitute bytes is a nonlinear operation. So usually you need a linear and some nonlinear operation. So sub bytes is a nonlinear operation where you take your input of 16 bytes. So this is 4 by 4. So this is 16 bytes. This is your input. You take a byte, you look up in a lookup table or an S box. It's called an S box. And then to the S box, you transform it to this is the input, this is the output of the S box, and that becomes your new 16 byte chunks. And then you do some shift rows, you mix the columns, then you XOR it with the round key, and then you go to the next round. So this is sort of the magic of the cryptographers to come up with this scheme. And then so at the end, you end up with something where you have a plain text, you do the 10, 12, or 14 rounds, and you end up with the ciphertext. And then here are different operating modes. So when you have a block cipher, you have this block. So everything is in chunks of 16 bytes. But what if your data is more than 16 bytes? So there are different operating modes, and then there's a electronic code book, cipher block chaining, and a counter mode, which are the most well-known ones. So ECB is the simplest one, where you take a chunk of your text, you encrypt it, and you get a chunk of ciphertext, and then you go the next chunk of your plain text encrypted, you get a next ciphertext, and so forth. And maybe you've seen this somewhere, or maybe you can kind of guess what's the problem with ECB?
See patterns in the block.
Yeah, exactly right. So the problem with ECB is exactly pattern. So if 2 input plain text are the same, you're encrypting them with the same key, the ciphertext is encrypted. And I should have included the really cool pictures when you take you have a picture, and then if you encrypt it with ECB mode, the encrypted data actually looks quite similar as the original picture because there's patterns. Like you have a white pixel will end up being some value, and a black pixel will be different value. So you can see patterns. So exactly. So in ECB mode, you can see patterns across the data. So most of the time, to defeat that, you use cipher block chaining or counter mode. So in CBC, you take your plain text, you XOR it with an input vector, then you encrypt it, then that's your ciphertext one. Then you use that uh, encrypted ciphertext, and you XOR the next plain text with the previous ciphertext, and then you encrypt that. So basically, even if there's a pattern here, between the blocks, there will be different XORs, and you break the pattern. The problem with the CBC is that it's very sequential. Like to do this encryption, I have to wait for this encryption to finish because there's a chain. So quite often we use counter mode, where in the counter mode, you take a counter, like 1, 2, 3, 4, 5, like literally a counter, you encrypt that, and since it's a counter, no two values are the same. So encryption of it, so there's 1, 2, 3, 4, 5. So you have different counters, then encrypted, and then so your plain text gets XORed with the encryption of the counter. So this is like a one-time pad now, and this is your ciphertext. So if you know your encryption key, if you know your counter, you can actually pre-compute the encryption, and just you do one XOR operation, and that's it. So these are different ways to encrypt the data with AES, and as long as you have the same key for encryption and decryption. So if we take a step back, and then if we think about confidentiality protection with symmetric keys, and how would you apply that to a quantum computing system? So this kind of tries to summarize that. Basically, any data, on the network, or when it's stored in the disk, can be encrypted and protected. But the things that you cannot protect is you cannot protect maybe this is a bit misleading. So you can protect the data on the disk, but you cannot protect it during computation. So when you want to compute on the data, unless you're using something like fully homomorphic encryption, you have to decrypt the data. So any data processed by the computers or by the controllers cannot be protected. Like I mentioned earlier, you cannot protect any of the analog signals because they're analog signals, are not digital ones and zeros that you can encrypt, and then you cannot do anything about the qubits themselves. So sort of symmetric key and confidentiality can be achieved kind of in these parts, but not on the quantum computer end. And then just as a side, for example, you can encrypt your program when it's stored over network. But for example, when you process it through a compiler, the compiler has access to your data and might be able to break the confidentiality. So this is a rough picture. I think just think about if it's on network or it's storage, the confidentiality is okay, but in other places it's not. Any questions about this picture or? Okay, all right. So for the last part, we'll talk about the integrity protection with hashes. So this is about confidentiality, making sure somebody or something doesn't modify the data. For integrity, we use cryptographic hashes. So again, on this list, so symmetric key, where we talk about confidentiality. Now we're going to talk about cryptographic hash functions for protecting integrity, which basically means detecting if somebody tried to or preventing somebody from modifying the data. So the cryptographic hash functions, it's really, I kind of think about it as a fingerprint. So a hash function sort of it takes a message of any size. So when you have a hash, you give it a message, and it essentially generates a short fixed length fingerprint or a hash. And some of the key properties are, for example, that even if you have two pieces of data that are almost identical, but they differ in 1 bit, that should produce a totally different hash value. So and then hashes are also one way. So that means if you have a hash value, you cannot given a hash value, you cannot reverse to the input. So when you talk about confidentiality and encryption, you have a plain text, you have a ciphertext, and then from the ciphertext, you can get back the plain text. So it's sort of, in that sense, somehow reversible. But in the hash functions, you cannot reverse them. So this is just an example. If you have Fox, this is the hash. We also call the hash we also call it the hash, the fingerprint, or the digest. These are different terms you use for the output of the cryptographic hash function. So that, input fox might give you this fingerprint. The red fox jumps over the blue dot, gives you this output, and then if you change red fox jumps, if you just change one letter or just one bit, the output is totally different. So you're supposed to be able to catch any one change in the data. And then so more formally, hash functions have a few properties. First one is the compression. So like I mentioned, it's a fingerprint, a fixed length fingerprint. So your message, no matter the size of your message, the hash function, the output will be the size of the output. It's much smaller, and it's usually fixed to like 256 bits, for example. So there's a compression, and the output is smaller and fixed length. And then again, given an input X, it's easy to find the hash. So it's easy to compute. You can actually compute this thing in reasonable time, but it's hard. So given you know, given Y, so given the hash value, you should not be able to reverse engineer and get what's the input. And then you also have this important property that it's not just important to give the one-wayness, but to prevent collision. So that means that, for example, if I have some message, if I know a message one and a hash of a message one, it should be hard to find another message two such that the hashes of the two messages are the same. So this is an example that, if I send one message, then you should be able to verify with a hash that that's the message. If I'm able to find a different message that has the same hash, then somebody could swap the messages during transit, but they would give you the same hash, so you wouldn't know anything changed. So this is also the weak collision resistance. And then the strong collision resistance is basically just finding any two messages. If I can find any two messages or bit strings that give you the same hash, then you basically have broken the cryptographic hash function, because the whole purpose is that this should be, short of brute forcing and checking, all the possible, 2 to the 256 inputs. It's hard to find. There will always be collisions because the hash is smaller than the input. So there exist many inputs that give you the same hash, but just finding them should be very, very difficult. And that's why the hash values, 256, 512 bits. So you have to kind of brute force, whatever, quadrillions of combinations of inputs to find it. And then there's an interesting, maybe as a last thing, related to this collision resistance, there's this birthday paradox. So basically here the idea is that sort of it might be surprising, like, if let's say we have a party or a class with a bunch of people, how many, there are n people in the room. What is the probability that at least two of them have the same birthday? And then the birthday paradox is that it's actually quite easy to have a pretty high chance of having the same birthday. So by the birthday paradox, if you have at least 22 people in the room, there's better than 50% chance that any of two of them will have the same birthday. So in general, this means that if there are some k possibilities, such as 365 days for the birthdays, there's an average square root of k. So you need to try a square root of k to find a collision. So if you have square root of 365 people in a room, then your chance of a collision is more than 50%. And then this means that this relates to this collision resistance, that unless there is big enough space of the hash values, you might just brute force and if the size of the hash was just 8 bits, 9 bits. If it was 9 bits, so if the possibilities, if there are 365 possibilities, then you would need only to guess 22, random inputs, and you likely find two two messages that have the same hash. So that's why. So because of the birthday paradox, we need to have a large number for the size of the hash. So So for each hash function, there are 2 to the n possible outputs or hash values, so usually 2 to the 256 or 512. And the reason the number has to be so large in part is just this brute force attack. So usually we pick n as something as 256, or now people are recommending 512. And then so so how do we apply this for integrity? So usually the way you usually do it is you have, the sender computes the hash of the message and then you send the message and the hash to another party, and then the person can recompute. Given the message, they can recompute the hash, and then if the hash matches, they're pretty certain that the message wasn't modified. However, if you just take a message and the hash, there's no secret key here, so anybody could change the message and then recompute a different hash and send that hash. So typically, to protect the integrity, you don't just hash the message, you hash it with some shared secret key. So, and then we call this HMAC, or hash-based message authentication code. The idea is that you hash both the message and the key, and there's this cryptographic construction where you don't just concatenate the message and the key and you actually take the key, you XOR it with a predefined output pad, and then you combine that with a hash of the key XORed with the input pad and the message. So this cryptographic constructions ensures that different key and different message will give you unique hashes. And then this way, only the person who has the key can generate the hash, and then only the person who has the same key can verify it. We'll talk about Thursday about digital signatures, where you remove the need for the shared key. But here, just as the symmetric key cryptography, you have the same key for the input and the output in a way. Yes, so the key is shared like an alias. Just an aside, you could use block ciphers as hash functions. So if you already have a hash engine implemented for some other purpose, you might be able to reuse it to generate the hash. So one way of generating hashes or fingerprints by leveraging a block cipher is to use the cipher block chaining. So remember, I mentioned that the CBC is not ideal because it's very sequential. You chain all the blocks together when you're doing the encryption, but so that's not good. But the good thing is that the last block depends on all the blocks in between and in the middle. So it's sort of like a result of all the computation. So this is what you could do. So you could take your plain text, you basically keep encrypting in the CBC mode, and then the last output of the CBC mode would be your fingerprint of the message. So that's one. This will be only 128 bits because the block size, so it's maybe not as secure as a hash function with 256 or 512 bits, but it's possible. So if you have a block cipher, you could use it for a hash function with a little bit lower security. If not, or if you have a dedicated hash function, usually well, it used to be SHA-2, now there's SHA-3. So SHA-2, again, well, yeah, almost 30 years ago, standardized in US. There's always some controversy about NSA being involved, so maybe some people don't trust it. Now there's SHA-3, which is a new algorithm, more recently standardized. But the key part here is that similar to symmetric cryptographic functions, it's not affected by Shor's algorithm. So as far as we know, you cannot use a quantum computer to break a hash function. And the best you can do is use Grover's algorithm to speed up the brute force search. So now people are recommending 512-bit hashes, because with Grover's algorithm that reduces to 256 bits, which is still quite a lot. So for both AES and SHA-2 or SHA-3, you don't have to panic about quantum computers doing anything so as far as we know so far. So and yeah, and SHA has again like AES, there are different versions with different hash sizes. So basically, the more bits, it means the bigger fingerprint, which means it takes more time to compute, but it's harder to break. And now there's Keccak, which was standardized well, okay, now 10 years ago. Uh, but so SHA-3 is a new type of cryptographic hash function. It's built differently than SHA-2. It has a much different construction, but it's also not affected by Shor's algorithm. So it's again, if you have SHA-3 with 512 bits, you're more than fine. So as a last slide, we talked about hashes. So how can they be applied to quantum computing systems to provide integrity? So very similar to digital encryption. Whenever you have something on the network or in the storage, you can compute the fingerprints of the data or whatever to make sure that it hasn't been modified. But similar to AES, to cryptographic ciphers, you cannot protect the classical computations while the data is being computed. It's changing. You cannot, okay, maybe if you hash the data at each step of the computation, you could verify some things, but it would be very impractical. Analog data cannot be protected, and then of course things that are on the qubits cannot be protected. So this is really the focus of the security study of quantum computers is really this right side where, let's say, the classical encryption and cryptographic hash functions are not useful. So we assume this is sort of taken care of. It's okay, it's done. But this is the part that really needs the help of protecting. Okay, so we're not much earlier than, but maybe 3 minutes early. Just to wrap up, yeah, we talked about different terminologies. Maybe some of it's a little boring, but it's good to have kind of this common vocabulary. We talk about different security policies, and of course the confidentiality protection with symmetric keys and the integrity protection with hashes. So on Thursday, we'll continue sort of these classical security topics. I'll talk more about public key cryptography, and then I'll try to start discussing the class projects. Okay, so let me stop the recording, and then yeah, if